costs and curves. It was basically an economics argument that if you were to compare the relative cost it takes to manufacture a semiconductor chip and trace it out against the number of components like transistors you would integrate on this chip, there was always a certain sweet spot. If you put less transistors on a chip, it would be more expensive, and if you put more transistors on a chip beyond the sweet spot, it would be more expensive. But at this point, it was optimal, and as the time went forward to 65 and then projecting to the future to 1970, this sweet spot was implying that you would integrate more and more transistors on a chip. And if you trace out those sweet spots, you would obtain a curve that has become known as Moore's law, which meant that as the time went forward, initially every year and then every 18 months, the number of transistors on a CPU roughly doubled. And the way we have spent this Moore's dividend, initially we got this performance. This enabled a larger software with more features. This also required larger development teams to maintain. To be maintainable, it also required more abstraction layers. And oftentimes, not every abstraction was zero overhead. There was often an attitude that because every year or every 18 months computers were faster, we could all abandon those hard languages like C or C++, and we can really just switch all to Java or C# and have memory safety and garbage collection because computers are faster anyway. And in the meantime, what has been in the background was the transformation hierarchy. Whenever we take a problem in our domain and we design an algorithm for it, only then we program this. When the program is translated by a compiler to instruction set architecture like x86 or ARM, and on a given microarchitecture realization like Intel Haswell, Intel Broadwell, Intel Skylake, this is where the program is going to be executed. Oftentimes, this transformation hierarchy was not only treated as the layers of abstraction, but it was treated as walls between those layers. If you were designing an algorithm and you would compare one algorithm with another, what you would be thinking about would be the asymptotic complexity of one algorithm versus the other, and it would be seen as bad practice and very special case consideration to look at the hardware costs of a given algorithm implementation when you compare one with another. In consequence, this phase one of Moore's law was essentially boiled down to maintaining walls between the layers. The abstraction layers were never to be crossed, and this separation was to be maintained strictly. The improvements in microarchitecture in that era were to a large extent transparent to a programmer. You didn't necessarily have to know the implementation details, and it was enough to say that computers were just getting faster. However, this trend has observed a first decay in around 2003-2004, whereas previously single-threaded performance was improving at a rate of approximately 50% per year. After that time, the single-threaded, single-core performance has been improving only at the rate of 20% per year. And the Moore's law didn't go away. We'll still have increasing numbers of transistors, but the reason that the single-threaded performance started to diminish its growth rate is that we have hit a power wall. At around 100 watts, the heating costs of the processor become prohibitive, and mainstream cooling technologies are often no longer adequate. So frequency scaling has become untenable, and the semiconductor industry as a whole has shifted to producing processors with the increasing number of cores, which meant that to extract this increased performance from the Moore's law that gave you more transistors, you had to start paying attention to multi-threaded CPU performance and multi-core programming. At the same time, while the processor performance has been increasing by orders of magnitude, memory performance has stayed roughly within one order of magnitude. And in more recent era, if you compare the latency, which is the response time of accessing memory, we can see that the best case access latency is still relatively constant now, since about a decade, it has stayed at around 15, 16 nanoseconds, and it hasn't been improving ever since. When we say that the memories are getting better, we often mean that we have higher capacity, and to some extent, we improve throughput or the bandwidth for your memory, but the response time is not seeing much progress right now. The emerging memory technologies that may offer some choice in the future are also mostly targeting the area between the disk, like the solid-state drive, and DRAM, like main memory, and they do not attempt to compete with caches or SRAM. So, at the cost curve scenario, we also see one inflection point. It used to be that you would be growing the number of transistors on a chip, and those transistors would be becoming smaller because it was the economic thing to do. It just made business sense because it was cheaper. And for the first time in history, at around 20 nanometer process, we have observed that the costs of decreasing the transistor size are now actually increasing. We no longer have the economic benefits of reducing the transistors to the extent that they used to hold since the beginning of Moore's law. This hasn't been without effect in the industry. The strategy of just waiting 1 year and buying next year's Intel's processor is no longer quite the same, because today the technology process has been extended to 3 cycles of process, architecture, and optimization. So you would have to wait longer and get less benefits. As a general comment, it is also not a bad idea to think of performance as currency. It's not necessarily a goal in itself. You may have entirely different goals. Your goals may be user features, user experience, good interface, immersive experience, dealing with large data, providing access to a lot of users, being able to handle many internet connections. All of these features that you actually care about, that your end users care about, are enabled by the currency of performance that enable you to get there. And as any other currency, you have a finite budget that you are able to spend. So it is the allocation of the decision of how you are going to allocate this budget to get the best experience to your users of your applications. So what is performance now that we think that it may be interesting? Well, if we go back to around 200 BC, we had a first example of matrix methods algorithms, like for matrix inversion when you have to solve systems of linear equations. Chinese mathematicians have invented methods called Fang-Cheng, operated on the counting board. Later, they were reinvented as Gaussian elimination, and because there were several methods to invert matrices, they were compared. And the way one algorithm was concluded to be better than the other is that you had to perform less operations on the counting board. So essentially, you were counting how many operations did you have to perform to conclude which algorithm was faster and which algorithm was slower. And if we go back to 1965, we see that there was a similar problem in the other abstraction called Turing machine. Once you knew you had a computable sequence and you had an algorithm that could be executed on this abstraction of a Turing machine, you would like to know which algorithm was better, which was more complex, which was less complex. And the idea turned out to be not really that much different from what was invented 200 BC. You essentially counted the number of operations performed by a multi-tape Turing machine. If a Turing machine had to perform more operations on one algorithm than another, you would classify this as the more expensive complexity class. But it was nothing else but just a glorified operations counting, just as in 200 BC. So we can see how this works in practice by using scientific method. We can observe the performance of our algorithm on a given problem size, scale up the problem size, scale up the problem, and see if we can validate the result with the prediction. We can use it actually in a very empirical way. Say, if you observe a performance of the algorithm and then you double the problem size and the running time doubles, you have a very simple heuristic rule to conclude you have a linear running time. At the same time, if you double the problem size and the performance running time quadruples, you have a reason to believe you have a quadratic complexity. So using those simple rules, you can come up with tilde approximation. Again, there is no reason to drop leading constants, for example. Asymptotic complexity has nothing to do with big O notation. It never had anything to do with big O notation. You can absolutely measure the running constants in your application, and you can reason about them as well. We can then consider the algorithms available in the standard library. For instance, find algorithm takes n, which is the linear order of time. And the way we think about this is that if you have a sequence of numbers and you are searching a number and it doesn't exist in that sequence, you have to go through the entire thing. So the complexity is linear in the size of the thing you have to go through. Alternatively, you could first sort the sequence using algorithm like introsort with log logarithmic complexity, and then on that sorted sequence you could find function lower bound, which itself only has logarithmic complexity. As a completely alternative way, you could use a container which maintains the invariant of being sorted, like std set, and then, because you have the invariant of being sorted, the member function of that container find is already able to use the logarithmic complexity find algorithm as well. So we can compare this for a few simple tasks using containers like vector set, flat set from Boost, and vector set from EASTL. How does it fare in practice when we benchmark this? So the benchmark is simple. We just generate a sequence of odd numbers, and then when we try to find a number, we just randomly look for randomly generated number in each container. And as we scale the problem size and analyze the performance of the algorithm, the common thing we can observe is that the ordering is rather drastic in terms of the standard set losing every single time. So if you compare the find method on the sorted standard set with the vector, which is copied to another vector and then sorted, then even if you measure the cost of copying and separate sorting, you are still going to be several times faster. You could also use a flat set container, which itself uses a sorted vector internally, and have a very fast lookup method in that container as well. And if you scale the problem size, the ordering doesn't really disappear. You'll still observe the same case, that the contiguous containers like flat set or even sorted and copied std vector are generally going to be faster than a red-black tree implemented by standard set. So how can we reason about features like that? How can we explain why one container and one find method is slower than another, and how can we find behaviors like that in our own common code bases? First thing to think about is that the algorithmic complexity itself is not going to be sufficient, but it is not enough to say that it is not sufficient. It is more useful to explain why is it not sufficient and what can we replace it with. So one of the reasons that the algorithmic complexity is not sufficient is that it assumes a random access machine. When it counts the number of operations and it counts the memory accesses, it assumes that every memory access at any random memory location costs the exact same time. And if you look at the costs as you scale the problem size and you analyze the prediction by the complexity theory using the random access memory model, relative to the running time, if this prediction was correct, every single algorithm should have a curve at level 1. However, as we see, algorithms which do some simple things like permutation, random search, or the binary search, as we have discussed, actually become increasingly expensive as you grow the problem size. So why are they becoming increasingly expensive? The reason is that the asymptotic theory means as the problem size becomes larger. And if your problem means analyzing data, then that means you have to have more data to analyze. And if you have to analyze more data, then you have to bring more data from the memory to the CPU. This means that you don't only have computational complexity that you have to be concerned about, but you also have to think about communication complexity. What is the cost of transferring the data from the memory through the cache hierarchy down to the registers in the CPU? Crucially, it is not enough to just summarize those numbers separately and say, this is the number of my transfers from the main memory, cache level 3, cache level 2, cache level 1. This is the computational cost, and just add those numbers up, because this is not how modern CPUs work. They haven't worked that way since the 1990s, when the superscalar execution and pipelines were introduced even in desktop computers. what they enable is overlapping this computation and communication latency. If you have an instruction that waits for data to return from the cache, you can execute a lot of other arithmetic and floating point instructions at the same time. The degree to which you can overlap those instructions or not can drastically affect the performance of your actual application. So it is very important to think about this overlapping and degree into which we can overlap as the key factor in measuring performance of an application. The reason this overlap is so important is that this cost has been widening because of the processor memory performance gap that we have mentioned. Today, if you have a latest Skylake Xeon series, you could, for instance, perform 32 floating point operations per cycle in double precision. And remember that cycle on a 1 GHz CPU is 1 nanosecond. Cycle on a 2 GHz CPU is half nanosecond. Cycle on 4 GHz CPU is a quarter nanosecond. So in a quarter nanosecond, you would be able, on a 4 GHz CPU, perform 32 floating point operations per second. Now think back to the trends we have seen in DRAM. The best case access latency to DRAM ever, assuming that you are accessing exactly the same row in your DRAM bank, and you have absolutely zero conflicts, you have zero queue delay, and the interconnect is infinitely short, would be 15 nanoseconds. So even assuming that the physics doesn't apply and the speed of light is infinite, you would still have 15 nanoseconds access latency purely because of those physical delays that you observe, compared to a quarter of a nanosecond for 32 floating operations. Which means that in 167 cycles today, you can do over 2,500 double precision floating point operations. And that means that if we look at the complexity of the algorithm and we only count the number of floating point operations, then we are counting something which is over 2,000 times less expensive than the memory accesses, which we do not count. So this results in the performance differences that we have observed. If we can take the contiguity into account, like using flat set instead of STD set, we can make our algorithm twice as fast. Similarly, even if you use vector and lower bound, this is going to be 3 times as fast as the standard set container, which is a node-based container, very cache-friendly, implementing red-black tree data structure. So this means that if you would like to reason about the performance of the application, if you would like to come up with a series of experiments and be able to twiddle them a little bit and understand how changing one thing in one code line changes the result in this way or another, we have to understand, at least on a basic level, what are the microarchitectural details of any CPU, because those are exactly the things that we are going to be playing with. So let's see how our instructions are processed when they go through a CPU pipeline. In the beginning, you can think of executing some function. And if you have a function call, then think about how did you get to that function. It was probably a jump. How did the CPU know whether this jump should have been taken or not? It was probably predicted by a branch predictor. So it's for a reason that the branch predictor shows up very early in the pipeline. And after we know whether we're going to execute a given function call or not, we are going to fetch instructions from the instruction cache. We are going to decode this instruction, take the immediate operands, if applicable, from the instruction in the assembly, put this in the instruction queue, reserve the entries in the reorder buffer reservation station, and schedule the instructions for the executions. So notice at this point, we were still executing in order, in the sequence of the instructions as delineated in the program generated by assembler. We have been able to already take care of the control flow, because whether the branch is taken or not taken determines what is the control flow of the application so far. Now, from this point on, when we see whether the scheduler is going to issue the instruction to the execution, we have a data flow dependency to consider. For instance, if you would like to add some memory value from location that lives in memory to a value that lives in the register, you have to satisfy this data dependency. You have to wait until the data arrives from memory, and only then you can schedule the addition instruction to fire and execute. So this is a data dependency instruction. data dependency order. At the same time, you are also constrained by the availability of the functional units. You have only so many ALUs if you want to perform an arithmetic instruction, like if you perform operations on integers or booleans, or if you would like to perform vector SIMD instructions, you only have this many functional units available. Sometimes you can perform simple integer operations while you are performing more complicated SIMD floating point operations at the same time. Then, if you are loading something from memory, you have to go through a load store port. If you do not have an available load store port, then you also will have to wait until the functional unit becomes available. So at this point, between the schedule and before the retirement of the instructions, they execute out of order, which means this is where the overlapping comes in. If you have some instruction that was waiting for the data dependency to arrive from memory, you may be able to fire up multiple floating point or arithmetic instructions at the same time. They will execute out of order, not in the same order they were in the assembly, but the processor at the very end will still have to make sure that they retire in order. So this retirement is the final step, the final hump in the pipeline when we are at this moment saying that this is going to happen in order. Everything between instruction schedule and the retirement happens out of order. So how can we measure the effects of this? How can we observe this instruction level parallelism in practice? One very simple example is to see what happens when we try to do some loop unrolling on the arithmetic instructions and data load instructions. So this is a very simple example when we have a data load. We are traversing a vector of doubles, and we are summing up every single element of this vector one by one. We accumulate those results in a single scalar variable called sum, and note that here we have to load this data from our vector at index I, and here we increment our running sum by the loaded value. At the same time, you could unroll this summation loop by a factor of 2, and what you're gonna do then is you're gonna have two local intermediate summation variables, sum1 and sum2, and you can think of first at every iteration summing up every even number and every odd number in the vector, and note that because you have been summing even and odd numbers 2 per iteration, you are proceeding with the iteration counter incremented by 2. And at the final step, you just have to collect those results by adding them up together. When we time the performance of this code, we will see that indeed the code without unrolling is going to be twice as slow as the code with unrolling. This is at the optimization level 2. It is using latest version of GCC, and it is using with the enabled architectural optimization options as well. So why is one code twice as fast as the other? Well, first step when we would like to answer questions like this is to fire up a program called perf, which allows us to do very simple profiling, collecting the performance measurement counters available on a CPU. And if we ignore most of the numbers, and I will just flip the slides back and forth, notice what is changing the most. One of the most changing numbers is the percentage of the front-end cycles idle. So remember, this part in the CPU pipeline, before we out of order execute the instructions, that part is still in order. That's the part when we are waiting for the data dependency. So it is in this part when we can already see that we have some stalls, that we are not running at the full potential, we are not running at the 4 instructions per cycle. And to see why, we can see what is the assembly code generated by our C++ code. So notice this is the summation running only one sum variable at a time, and this is the assembly code. So you can see that the main part of the loop is here. We have the load operation from memory. We add this to the sum variable, which is stored in the register XMM0. We increment the loop counter by 1. We compare this with the number of the elements in the vector. And if the loop counter is still not equal to the number of elements of the vector, then we just look back and we continue this iteration by iteration by iteration. At the same time, we can see what happens if you are going to have two local variables, sum1 and sum2. We are going to see that we have still addition of scalar double precision register, but now we have register XMM0 summing up all of the even numbers and register XMM1 summing all of the odd numbers. Then we advance the loop counter by 2. Just as before, we compare the loop counter with the total number of elements in our vector. And if the two numbers are still not equal, then we loop back and continue the iteration per iteration per iteration. Only at the end, when we have collected those partial sums of all of the odd numbers and all of the even numbers in registers XMM1, XMM0, we collect them finally to register XMM0, and this is what we return. So notice that we were executing the same instructions in the assembly. The only really difference was that we had one scalar double precision addition running on register XMM0, while here we had two addition instruction, still scalar, still double precision, but they were running completely independent register XMM0 and completely independent register X1. Register X0 didn't have to know anything about register 1 and vice versa. This independence is what enables parallelism. And the way you can see how it enables parallelism is we can drill down a bit deeper using Intel architecture code analyzer. So this is the fragment of the code we are interested in. We have some 1 and some 2. We have noticed that one is using 1 register and the other one is using 2. And the one that was using 2 registers was running twice as fast. Why is it running twice as fast? Let's analyze this using the Intel architecture code analyzer. We can compile the program, run this under control of the analyzer. And now, this is something I run on Sandy Bridge, okay? So in Sandy Bridge, what we have is only 2 load store ports, and we have 3 ports capable of performing arithmetic operations. This is all I have, okay? So notice that at the bottom here, you are going to see this exact same assembly code as we have seen before. But now, notice that those ports you can see here, ports 0, 1, 2, 3, 4, 5, are exactly the same ports as you can see here from the Intel manual to your CPU. So just comparing the documentation on your Intel CPU and the results from the Intel architecture code analyzer, you can see which functional units your CPU is using when you are executing the code that you have. And in this case, we can see that this addition instruction that was using this 1 XMM0 registers was on the critical path. This is what we pay for. This is what is going to drive the latency of our application. And we were not really making use of the addition operations that we are capable of on this CPU. Some of the ports went unutilized. Now notice what happens when I change to the code that was using the 2 registers. In this case, what we are going to do is to analyze the instructions and remember that we are adding up all of the odd numbers and all of the even numbers. So we are now using the register XMM0 addition. We are using the XMM1 addition. We are also having to compute the index corresponding to the odd numbers. This is also an addition operation, which we may have to pay for, but it is still free. This is still fully overlapped. And at the end, just as before, we have to perform a comparison. And you can see that this comparison is actually also utilizing a execution port. It is going to be port number 5. You see this port number 5 here. It is labeled with ALU, arithmetic logic instruction. It is labeled with JMP, which is jump. And if you notice here, what is going to happen, you will see that the number of operations is 0, and you will see F. This means that those 2 operations at the end were fused. So in fact, this compare and the jump instruction is effectively fused to 1 macro operation that is executed just as 1 instruction internally in the CPU. We don't pay for this extra. And what is also nice is that we are now able to overlap those additional operations because we have enough functional unit to perform both the addition on the XMM0 register using 1 ALU functional unit, then additional XMM1 register using another ALU unit, and then the subtraction we need in order to compare the loop index with the number of elements in the vector on the 3rd functional unit. So we are utilizing all of the functional units that we have. Note also that from this point on, I can already tell you, and I think you can probably see it too, that unrolling our loop further will not help. Why doesn't it make sense to unroll our loop even further if you look at the code analyzer output? Yeah, we have pretty much utilized all that we have. And remember that we also are utilizing the load ports because we have to load those data from, at this point it would be caches because it's going to be std vector, it's contiguous, it's very cache friendly, but we only have 2 load ports. So also, but as you said, we also have no more functional units, so even if we had a more complex CPU with more load ports, there's only so many operations you can unroll. So this is a very simple way of measuring things and seeing whether there is any potential improvement left. So it is also very useful to know what is the point at which we should stop optimizing, even before you devote any extra time for this, and even if before you start profiling and measuring whether it is taking 2 minutes or 3 minutes, sometimes the measurements themselves may take you a full day if you work on very large data. This is fully static. This is only need to compile the application and run it once, and you will collect this utilization of functional unit data. So it is a relatively fast process, and you can see if you are at a point where you should stop your optimization, or at least you should not count on any dramatic performance gains just because you are utilizing the functional unit more. So Code Analyzer also enables us to show this graphically. You can see here, when we look at this addition on a single register and this comparison operation, which really involves subtracting the index counter from the total number of elements in the vector, our instruction level parallelism at this cycle is 2, because we are only able to execute those 2 instructions in parallel. Whereas when we utilize more functional units, when we perform the addition running over XMM1, addition running over XMM0, and compare of racks and the source index register, then we are able to have 3 operations in parallel. And those speedups mean that we are able to achieve higher instruction level parallelism and execute more work in the same number of cycles, and hence observe faster execution time of our program. And if you would like to have some way to reason about it, there's actually a classical parallelism work called the work span law, where you basically count the number of operations you have to perform in total. This is work. And then you divide it by span, which is the length of the critical path, the longest path of the operations that cannot be overlapped with anything else. So in this example, notice that you read this tree exactly as you would read this graph produced by the Intel Architecture Code Analyzer. So you can see if you are able to perform the same amount of work, but if you are able to shorten the critical span by moving some operations to be overlapped in the same cycle with another operation, you are going to increase the instruction level parallelism and proportionally decrease the runtime of the application. So the work span law is essentially just a formal way of reasoning about the results that you are going to get from the code analyzer from Intel. And this can be limited, of course. So one reason that our loop without unrolling wasn't executing in parallel is that we had a data dependency. Every single time we wanted to add new value to this register XMM0, we had to know the old value, meaning that we couldn't just increment this XMM0 in several functional units at the same time, because they would just be stepping over each other and producing garbage. So it really is important to think as the data dependency as the limiting factor of the instruction level parallelism that we can achieve. If we have just one operation, like this XMM0 addition, that always needs its result before it can produce the next result, then the instruction level parallelism is 1 on this operation, meaning no parallelism, because we can never overlap it with another copy of itself, even if you have a very wide superscalar out-of-order execution CPU. In contrast, if you have operations like this, then you get more benefits from the superscalar out-of-order CPU, because you have completely no dependencies between the XMM0 addition and XMM1 addition, so you can achieve the instruction level parallelism only limited by what hardware gives you. So now, the other thing to care about is that this may be more important or less important depending on how expensive this non-overlapped operation is. If it is a very, very long data cache miss, and you cannot overlap it with any other operation, it's going to be more expensive in your program than in the case where in your program you are surrounding this with a lot of simple independent instructions that you can execute at the same time. And this is, I think, a critical point here is that you can really see that this is where this overlapping comes in, because we cannot just count the operations in isolation. It really matters what is the exact instruction stream in your program, because it is this instruction stream that is going to determine what is going to be surrounding this long latency operation you are worried about. If you have nothing surrounding this long latency operation, then your overlap with just 0, and then you will have no instruction level parallelism. But if you have a lot of independent simple operations, then those operations are what you are able to execute at the same time. Hence, you have to really think about the instruction stream of your program, your assembly language generation, and your instruction level parallelism to reason about performance of the algorithm implementation being fast or slow. Now, to put this up in the graphical terms, the way to classify this in general is wasted slots. So on the modern Intel x86 CPU, in total we can think of executing 4 instructions per cycle as the ideal perfect case if the world was awesome and if everything was costless. Now we always deviate from this, and the degree to which we deviate is called empty issue slots. And there are 2 ways we can think about this. What we have observed when we are running this one addition on this integer, and all of the other slots were being unutilized because we didn't use any functional units in that cycle, was called horizontal waste. So you can see, you can think of this as having those 4 issue slots, but you only utilized 1, for example. In contrast, if you are able to perform more operations in this cycle, the horizontal waste disappears. But there's also another class of problems, the so-called miss events. So in this example, you may have an instruction which depends on data which has to be loaded from memory. And before you are able to execute this instruction, the data has to arrive, and you will wait longer if this was a cache miss. So this is called the vertical waste. And by analyzing both the cost of the vertical waste, cache miss events, branch miss prediction, page faults, ITLB misses, together with the horizontal waste, which is degree of instruction level parallelism and memory level parallelism, you can think of this basically as a game of playing Tetris. You would like to fill up those slots as best as possible and minimize the empty unutilized ones. So there are a lot of causes of those wasted slots, but graphically I think it's easy to show them like this. You have this full utilization of 4 instructions per cycle in the ideal world, and then in the real world you, for instance, have a branch misprediction. At this point, when the branch is mispredicted, remember the CPU doesn't know what to fetch from the instruction cache. And if it doesn't know what it fetched from the instruction cache, it doesn't know what to execute. If it doesn't know what to execute, it's not going to execute. So the instruction per cycles will drop to 0. At the same time, if you are going to have a data cache miss, and the instruction needs that data to arrive, the instruction also is not going to execute, so you also will have 0 instructions executed per cycle. And depending on whether this was something like a branch misprediction or a data cache miss, this penalty may be lower or larger. This is also not the only thing that matters, because what also is important is how long is it going to take you to recover from this cache miss. Because if your code exhibits generally high degree of instruction level parallelism, you will recover faster as well. At the same time, if you have a lot of independent operations that you can still execute while the instruction window drains as you wait for the cache miss to return, the instruction per cycle drop is going to be alleviated. So by looking at the time it takes to drain the window, which depends on the number of independent instructions before the cache miss events, the particular nature of the miss events, whether it's data cache miss or the branch miss prediction, and the instruction level parallelism of the code that you return to after the miss event is serviced by the memory hierarchy, you can think of the breakdown of the components of how expensive those miss events are in practice. And we can also measure those things using a tool called Liquid. So for example, going back to our summation example, we can see that the way to express this, for instance, is to measure the floating point operations for the summation of one variable, summation 2. And what is also nice about this tool is it allows you to very quickly test effects of auto-vectorization. So auto-vectorization didn't happen because we didn't ask for this. And in order to ask for the auto-vectorization of this code, we can use the flag tree vectorize in GCC. By itself, this flag is not enough, because when we perform floating point operations, generally addition of floating point number a plus b plus c produces a different result than adding c plus b plus a. And if you vectorize, you assume that those addition results should be associative. So we have to tell the compiler that we are fine with breaking the floating point standard at this point. And the way to tell compiler that we are fine with taking the risk of breaking the precise floating point standard is to use the flag fastMath. And when you do that, you will see that the auto-vectorizer has worked. We can measure this by the scalar and non-vectorized operations being reduced to 0. And every single floating operations in this code that matters was executed as a VX operation. So this is a very quick way, even without looking at the assembly. Maybe you have a code base which is 10,000 lines, and you really don't have the time to look at every single assembly line generated from those 10,000 lines. You can just run this program once, look at this table, and just by looking at this one line of code, which tells you what is the AVX number of operations, and the last line of code, which is the scalar number of operations, you can immediately see, did the auto-vectorization work or not? Should I drill down any further, or am I fine right now? So this is a great time saver, because oftentimes it is not realistic to, as much as we wish we could, to examine every single assembly line of code. And if you are using Windows, if you are not using Linux, it doesn't matter. Sometimes people say that you need vTune for this. You do not need vTune for this. Remember that performance measurement counters that enable this are on the CPU. So first of all, you could program this. It is documented in the Intel software development manuals how to set up those standards in assembly. But if you don't want to deal with assembly, you can download a freely available Intel PCM, which is Intel Performance Counter Monitor, which allows you to put this measurement in your C++ application. So if you have a fragment of code that you are concerned about and you would like to measure the number of the cache misses in this function or the number of the branch misprediction in this function, you can just surround this code with the function calls to the measurement in the Intel PCM, and you are going to be able to exactly track how well is the code performing with respect to cache misses and with respect to the memory accesses. So this tool is available. It's cross-platform. It's not just Linux and Windows. It's also Mac OS. It's also free BSD. And it also ships with a very nice example application called PCM Core, which, even if you're running on Windows, it actually has a syntax very similar to Linux perf. You can just run it and tell it what event your CPU measurement counter should be measuring. So if you are concerned about the misaligned memory accesses, you can actually use the exact syntax you would be using in perf. Just press enter, run your application, terminate it, and see what was the result of the measurement counters. So this is also enabled in this freely available PCM. Now, we can see that as we collect those results, we can think about how to model them. And to put this in a summary equation, one could say we can see that we can break down the execution time of our program by considering not just the instruction count, but also how many cycles on average our instructions take to execute, given also what is the cycle time of our CPU. Remember, 1 GHz CPU, 1 nanosecond cycle time, 2 GHz CPU, half nanosecond cycle time. This is essentially given. What we can control is the instruction count and the instruction miss, and what we can also control is how expensive are the instructions that we use. And how expensive instructions are depends not only on the CPU cycles spent per instruction or execution, but also on the number of the CPU cycles spent on accessing memory in that instruction. And the number of the cycles spent accessing memory depends on the locality, because it tells you that the instructions which are mostly going to access data from cache are going to be less expensive than instructions that will have to chase pointers and go often to the main memory. So just by simply breaking down this CPI instruction, clocks per cycle, into the instructions count, and then looking what the cost of instruction depends, and analyzing both the CPU cycles and the memory access time cycles, you can already have some idea how to reason about the big picture of the time it takes to execute an application. And it's not only if you are caring about performance in terms of the execution time. Oftentimes, if some of you are cell phone programmers, what you really care about is the battery time, because battery time directly translates to the user experience of the users of your application. If you just drain battery after 5 minutes, the user experience is known as poor user experience. And what is interesting is that the power also depends on the energy per instructions and instructions per second. And if you look at the datasheet tables of energy instructions, you can see that there is also orders of magnitudes difference in terms of the joule drawn of power, whether you use registers or whether you use cache, or whether your instructions travel to the main memory of chip. So data cache access matters not only if you care about the time it takes to execute instruction, but also if you care about saving energy. Because, of course, accessing far away main memory that lives on chip is going to be more costly in terms of power than fast registers or level 1 cache that lives on the same chip. Similarly, if you are writing a graph processing application in the old days, a popular benchmark was the so-called traversed edges per second. And the problem with the traversed edges per second benchmark was that, again, it was just glorified counting of operations. It didn't take into account how expensive it was to travel across a particular edge, and how expensive it is to travel across a particular edge depends on what is the locality of the edges that led you to that edge. And you can have graph algorithms that look very similar to what the linear algebra look like, because the layout of your graph, if you have something like the depth first search or even the breadth first search, can be laid out exactly in the order that is going to match the traversal and is going to increase the contiguity, meaning that some graph traversals algorithm may be faster, even though they traverse theoretically the same number of edges, only because you have carefully laid out all of the edges and the vertices data to be adjacent in the memory that is going to be accessed in the traversal process. Finally, this also gives you a budget. It tells you what you are able to do and what you are not able to do. For instance, if you are using mainstream, today even low-level consumer class commodity Ethernet card, those are often 10 gigabit Ethernet cards. And say you would like to do packet processing of the Ethernet packets on that card. If you have a CPU with 2 gigahertz, you are going to have roughly 130 CPU cycles per one packet. If you would like to maintain guarantee that you will not be dropping any packets, then 130 cycles is what you have. And now remember that one cache miss that has to travel to DRAM, main memory, is about 60 cycles. So if you have 2 cache misses that have to hit main memory, you already went over budget. And this already tells you that if you are writing a network processing application and you care about not dropping any single packet, then this is your real-time bound. You have to satisfy 130 clock cycles budget, and misses in the caches will not enable you to satisfy this time frame. So this cache hierarchy access means that when we look at the cycles per instruction, we shouldn't assume that we have infinite cache and every instruction takes the same amount of time to execute. The amount of time the instructions take to execute depends on the number of the misses per instruction. And the more misses we have in our instruction stream, the longer the cycles per instruction become, and the longer the execution of the application is. Overall, then we can see how those effects are combined together when we have pipeline level parallelism, instruction level parallelism, and memory level parallelism, because as far as cache access is concerned, there is a very similar feature to what we have seen in instruction level parallelism. Just as we had addition done over one functional unit and 2 functional units, we can have cache misses operations which are initiated in parallel or which are initiated one after another. And you will see if you only have one cache miss, that then needs to be serviced before you can service another cache miss, that needs to be serviced because before you access another cache miss, you have only one degree of memory access stream, so you have no memory level parallelism. In contrast, if you can issue multiple cache misses in advance as you proceed with your computation stream, some of those cache misses are going to be costless for you. So again, it is not just the number of cache misses that you are concerned about. The number of cache misses is irrelevant for execution of your applications. What is relevant for the time of your application is the number of the cache misses you couldn't overlap with anything else. So let's see how we can analyze this. And the reason we care about this is that when we transfer data from memory, we cannot just access a single byte. We always have to bring entire cache line from the memory, 64 bytes on Intel, for example, which means that whenever we have a data structure which is just scattered around in memory, chances are we are just going to be bringing lots and lots of cache lines, and then we are going to be wasting most of those cache lines, taking 1 byte at a time from every single one. So what we are concerned about is locality, and the reason we are concerned about locality is basically the degree of utilization of every single cache line. The more useful data you have in your cache line, the less expensive in practice the cache miss becomes to your application. And on the flip side is the less useful data you have in every single cache line that you have fetched, the more expensive the cache misses become for you. So again, it is not just the number of cache misses, it is the number of cache misses relative to your application and relative to what you're going to extract from every single cache line as you proceed with the computation. And we can see the impact of this in the standard containers. For instance, let's start with pointer chasing example, first with vectors. So notice that this is still pointer chasing, even though vector is actually my favorite container, it is contiguous in memory. If you would like to go through this vector and some elements, in the beginning, if you think about the implementation of std vector, you still have a pointer to data. So first you have to chase through that pointer to data. But once you have done this one level of indirection, you are fine, because then you are going to be in the memory when you're going to have the data elements laid continuously one after another. So you only had to chase one pointer jump, and then you have nice, beautiful, contiguous layout, and every single cache line is going to be packed with useful content. So vector is very good in this case, all right? In contrast, we can look at the singly linked list. So notice this is the exact same code. Here we also traverse the list and sum up elements in it. But here we had to take the pointer to the next node. And then we are in the next node. We're able to extract this item from that node. But then we have to jump to a completely different location in memory before we can extract another data from that location. Of course, those pointers on x86 64, pointer is going to be obviously 64 bits. 64 bits is 8 bytes, and every single cache line is only 64 bytes. So remember, those pointers are also going to add up to what you are going to be able to pack in every single cache line, which means that if you switch to a container like doubly linked list, you are going to have 2 pointers. You are going to have one pointer to the previous node, you are going to have another pointer to the next node, and only then you are going to have the item. So not only you still have to do the pointer chasing and you are incurring cache miss on every single access, but you are also having less and less useful utilization of the cache lines. And the common feature of those node-based data structure is that we always have to get the pointer to the next node before we can dereference this pointer and follow on to the node after that. So notice this reminds us of something, because this is very similar to this serialization of the execution we had. In the beginning, we only used one register xmm0, and we had to always know the previous value of xmm0 before we added next value to it. So in this case, that was a pure example of only instruction level parallelism being 1. In this case, the reason instruction level parallelism is 1 for a structure like linked list is because the memory level parallelism is also 1. We are not able to initiate multiple cache misses in parallel because we always need to know first the value of the next pointer before we access the value of the next pointer after that. There is no way we can predict what those next pointer values are going to be in advance, and because of that we have memory level parallelism constraint to 1, and because of that we have instruction level parallelism constraint to 1. So just like the data dependence in the addition of the simple vector elements to registers can determine performance, data layout can also determine this. And the way to analyze this, we can look at the forward list. Again, we have this assembly generated code. Notice that here we have this dereferencing of the pointer to the next node. Then we load the address from that. Then we compare this address to 0. If it is, then that means we have hit the end of the list. This corresponds to the null pointer, and we jump out of the loop. Otherwise, if it is not equal to 0, then we compare with the element we are searching for, like if you are using a simple find operation, and then you loop over, and this pointer chasing exactly corresponds to this pointer chasing here. So every time you load this address to the accumulator register, then you dereference the accumulator register before you can jump to the next address, and on and on and on. So this is fully serialized with the entire path being the critical path, because you cannot overlap this with any other cache miss operation. And this is how it looks in assembly if you just show the assembly side by C++ code. You can use very nice debugger called Radare. It is about 10 years ahead of GDB. I would fully recommend you to take a look at that. I could give a 2-hour talk talking only about Radare feature. What I love about it is that we don't have to show the code just like this. So notice what we can see here. You can already see that we have some loop structure here, showed with the arrows. We have this dereferencing of the pointer to the next node when we dereference the address stored in the accumulator register racks. Then we move it to the racks, we test racks against 0, and then we jump if this is equal. But this is still flat. So what Radare allows you to do is to actually construct the control flow graph of your application the way it looks in assembly. And every single node on this control flow graph is a basic block with single entry and single exit. And the reason I talk about it is that processors love basic blocks. This is the domain from which the instruction level parallelism is extracted. The more you have basic blocks without data dependencies, the more parallelism you can extract from this, the more operations you can execute out of order in parallel, and the higher ILP becomes. So by looking at the control flow graph and analyzing the basic block structure of your code, you can already very clearly see what is going on. And this again will, I think, remind us of this example we had in summation with this single register. So notice this is the pointer chasing loop part. When we have this pointer, we load the value to the register, we test it against null, and then if we are not done with the loop, we are going to see if we found the number, and then we branch over. So you see, this is the same critical path problem when we had this full serialization when we had seen before. Before we can initiate next iteration of this pointer chasing loop, we have to know the value of the previous iteration. You cannot jump several nodes ahead. You only have to know dereference those nodes one by one by one. And this leads to a natural analysis of this problem. The problem with the node-based data structure is not that they don't utilize cache efficiently, but cache misses are more expensive for them because they are isolated. They cannot be overlapped with anything else. In contrast, if you were traversing, for instance, multiple single linked lists, then you wouldn't actually pay for those cache misses more because you could, for instance, overlap 3 cache misses for traversing 3 single linked lists at the same time. And this overlapping can be usefully exploited in our case. The way we can exploit this is to have our own data structure which allows us to think ahead, to see what those future nodes' values should be. And this speculation is called prefetching. So what you can do is you can remember the addresses of every single node in the data structure, and then you can, for instance, skip 3 or 4 nodes ahead. That's why this data structure is called a skip list, because you are skipping several nodes ahead. And notice if you skip several nodes ahead, this is a little bit like traversing multiple linked lists, but you can just see off traversing one fragment, initiate cache miss to have another fragment prefetched into caches, and then have another fragment prefetched into caches. What you can also exploit this is the so-called multi-stage prefetching, when the closer nodes are prefetched to the L1 and the faraway nodes are prefetched to the L2 cache, which enables you to have some adaptive prefetching aggressiveness. So when you would like to do something like that, you can start by just doing a linked list with the jump pointer arrays, and the parameters that you care about are basically the distance of prefetching and degree of prefetching. So distance is how many nodes you are going to prefetch in advance. If the distance is, for instance, 4, I'm going to prefetch 4 nodes in advance each time I move one node next. Degree is how many nodes you prefetched in total. So you can prefetch, for instance, 2 nodes at the same time, or you can just prefetch 1 node as you are traversing, depending what is the size of the node, what is the size of the data item relative to the cache line. Different numbers make sense. And if you decide on this, what you care about is to balance. You don't want to prefetch too far away in the future, because you may not be able to usefully overlap this, but you also don't want to prefetch too close to the node you are currently in, because you may not have enough computation operations to overlap with the memory service time. So as you try to balance this, you don't have to just guess, you can measure this, and the metric to measure is the level 3 and level 2 utilization. So what I would do in the code like this is to basically have a prefetching with a degree that I can configure. This is the parameter D, and then vary this parameter, and also vary the aggressiveness in terms of the degree, how many nodes I'm prefetching. And then as I measure this over different distance of prefetching and over different degree of prefetching, I can measure the utilization of my level 3 cache. And we can see that when we look at the timing of our application, we started from 28 times units, and 94% of level 3 misses were, level 3 accesses were cache misses, so we have been missing in the level 3 cache 93% of the time. But as we calibrate the distance, we can make this application twice as fast, and then if we measure the cache misses in the level 3 cache, we can kill this also to half, to 56%. So notice that this is basically the metric to look at when you calibrate the aggressiveness of the prefetchers, how far ahead you should prefetch, and how many fields you should prefetch. Just track what happens to the level 3 cache miss ratio, and what will happen to the cache miss ratio will very closely correspond to the execution time performance scaling that you will observe. So every single thing that we have seen, I think here was basically the underlying message is measure, measure, measure. And it is important to know what to measure. For instance, for prefetching, the whole reason of prefetching is that you want to speculatively initiate cache misses in the future. So you have to measure the cache miss rate. And that's basically the overall takeaway. There's lots of backup slides available online, so I think I will just... I always have backup slides. I will just jump to the conclusion. So first of all, there's lots of useful features in C++ standard, in C++ 11 and C++ 14. For instance, scoped allocators with stateful allocator support. Constant expression, very useful. Hardware interference size is very cool. It may sound weird, but this is basically the way to have portable information about cache line size. And not every CPU like Intel has 64-byte cache lines, and usually before that we had to just hard-code macros and make sure that each time we compile application on something else, our macros of cache line size were still correct. Now we finally have a portable way in C++ 17 standard to just ask the compiler what is the target architecture cache line size. So that's already very convenient. There's aligned allocator, which used to be in C11. In C++ 17, C11 standard library is incorporated to C++ 17 standard. So this is the first time C++ actually gets the scoped allocation in the standard itself. We also have very nice data structure called string view, which is essentially a zero overhead interface similar to std string, but acting just like the C-style pointer to the character, which is also something I would recommend for the high-performing code. Overall, the takeaway is that we should measure because what is costly and what is not costly depends. And the one general answer is if someone asks you, is this feature fast, is this line of code fast, is this algorithm fast, the one correct and honest answer is always, it depends. And for instance, is the cache miss expensive? It depends. The miss penalty has nothing to do with the number of cache misses. It was important to look at the number of cache misses in the 1980s, but we do not live in 1980s anymore. Processors that we use today are superscalar, multicore, support hyperthreading, and they can overlap those cache miss operations with a lot of computation operations. So the cost of cache miss depends on how many operations we can overlap in our application. And the overlap depends on how many of those operations are independent. Do we have good instruction level parallelism? Do we have good memory level parallelism? This is the driving factor of the cache miss cost. And we can then use this to balance this cost to try to speculate away from this using prefetching, for example, and track what happens, for instance, to the level 3 cache miss rate. Branches are another interesting topic that we didn't have time to go through. Branches, again, it doesn't matter how many branches you have in your program. And just a side comment, virtual functions, they are just indirect branches. So everything that applies to the cost of indirect branches applies directly to the cost of virtual functions. The penalty for branches or the penalty for virtual function costs depends. Is it predictable branch or not? If the branch is predictable, you may pay nothing. And the branch predictors in modern CPUs are pretty good, actually. If the branch is not predictable, then the penalty depends on how long is the branch resolution time. How long are you going to take to recover from the branch miss? And how long are you going to recover from the branch miss, again, depends on the surrounding code that is before the branch and the code that is after the branch. You will recover faster if your code is good, if the code has high degree of instruction level parallelism and high degree of the memory level parallelism, then you can at least reduce the cost of unpredictable branch by recovering faster from that branch. Also, you can often trade off, if you know that you have unpredictable branch, you can use conditional execution, and in this case, you convert the control flow dependency to data flow dependency. Again, is it better? It depends. You should measure, you should track the utilization of your functional unit, run the Intel architecture code analyzer, and see which one is better on your particular code example. Overall, the lesson is to take the features of hardware into account when you think about your application. Take into account the large variety of the instruction level parallelism, memory level parallelism, pipeline level parallelism, and break the layers. We don't have to think about just one level of the transformation hierarchy, but several of them. And in general, this division between hardware person and software person also needs to go, because I think when you're interested in high-performance software, you're also interested automatically in hardware. Thank you for coming to my talk.